Yeah, thank you. I'm Jan Sommer from the German Aerospace Center. I work at the Institute of Software Technology, and there I'm the deputy head of the Department of Flight Software. And today I want to present our new project to you. We just had the kickoff last couple of weeks ago, and it's called Stellar Apps. And we want to do like a new approach from our current technologies. So we want to have something like an app store, but without the store part. That means we want to enable the secure, efficient, and flexible use of the onboard resources of our onboard computer. Or
I need to interrupt. You're not sharing your screen.
Okay.
Remotely.
We'll get this.
Eventually.
This includes then also a software development environment for them. So. Okay, thanks. Then, so where do we come from to that we want to do that? So there was the Nebula study by the Keck Institute for Space Studies, and so the gist is that currently we often operate that we have sensors or instruments on board of a spacecraft. We generate some data there. We download all the data and process this one then on ground, or at least the scientists, not me. And now the newer generation of instruments creates an enormous amount of data, but the bandwidth capabilities have not grown with this kind of data sets. And that's why we will need to either scientifically pre-process the data on the onboard computer, or at least select the data which are interesting. And the idea is that we have some data retention on board. So like in data archive, we only send a certain amount of, let's say, determined interesting data sets to the scientists. And if they then say, okay, other parts might also be interesting for us, they can download them on demand, but it's not possible to download all the data anymore. So with this kind of mindset, we then want to leverage other parts. So that means short time to orbit, execute complex applications in the secure environment, and help them then in turn to incrementally improve their algorithms which do the selection later on. We came up with a couple of use cases inside of DLR. They are mostly research centered. So one is, of course, the autonomy of health management, especially for constellations where you look at the housekeeping data of your own satellite and also the neighboring satellites to determine your overall health of the system and see if any action needs to be taken. And then, as I said before, we have the sensor data pre-processing and scientific processing on board. We want to look at simulating digital twins so that we can test our ground operations for, let's say, a simulated constellation. And another thing is real-time processing of Earth observation. So, for example, if you have an infrared camera which detects the wildfire. You directly send a short message to the ground crew outside of the regular contact schedule with your ground station so that they can prepare the necessary actions when the next ground contact arrives, or book a new one. That could also be possible. And last of our use cases, which we have with the robotics people at DLR, is having optimal navigation for on-orbit servicing. So you have to navigate your robot arm to move and, let's say, unfriendly target, or at least a target which is not cooperating, and you have to process a lot of image data for that. So we started a couple of years ago with the SCOSA project, which aimed at fulfilling these kind of use cases. It's now prepared for a mission, and there the goals was that we create a network of nodes, some reliable, some commercial parts which are not radiation tolerant, and then in case we detect a failure of one of the high performance nodes, we can reconfigure the system and redistribute the workload. We have then developed some data-driven programming models for this data management, and also for reliable messaging across the nodes and detecting the health of the network. And this allowed us then to also implement fault tolerance mechanisms to isolate errors and also have checkpoints. So if we want to redistribute application tasks, we can do so and don't have to can start with the last checkpoint we took. So in the right, you also see a picture from the current EMV campaign, which is conducted just like 2 weeks ago or something. So how does the reconfiguration work there? So in case one of the, let's say, high performance node has a single event upset and is not performing anymore, we detect this in the system, isolate the node, redistribute the tasks, and then can still offer the service, maybe with some performance degradation, but at least it's still operational. And at a later stage, with the ground crew maintenance window, we might reboot the node, add it back to the network, and reassign the applications to the node. The software stack is, for the reliable node, it's basically an Artemis operating system. And for the high performance nodes, it's embedded Linux. We use SpaceWire for the inter-process communication and inter-node communication, and use several libraries. For example, the Outpost library to abstract away the operating system, so that our services usually are then implemented in the same way for both operating systems. And also we have implemented the distributed tasking to allow this communication, that one application can inform another application about data without knowing on which node it actually resides. Both of these libraries are also open source, so if you want to have a look at this, you can find them on our GitHub pages. So currently, as I said, we are preparing for the satellite which carries the SCOSA experiment. We have a 9-node computer. That means 8 Xilinx Sync 7000 based nodes with each 2 cores, and 1 GR712 with 2 Leon cores. So in total, 18 cores, and it's mounted in a CubeSat of 12U size and will be launched next year. And we want to basically then use this as a demonstrator platform to demonstrate the reliability of this kind of setup, and also give the computing power then to several applications we developed within DLR. And our expected lifetime is 1 year for the main mission, but we want to use it also for an additional year later on. And this, we come to that later on. So lessons learned during the whole development phase. Yes, there's always the conflict. The application developers want to install their own custom libraries and their own runtimes, and the software integrators, which have to bear the responsibility for the safety of everything, don't want them to do that. And that means we have this conflict there, that they want to have especially the same libraries they use on ground, because they are not necessarily always starting for an onboard computer with their applications. and yeah, we still have the old software safety standards we have to apply to the full software. And we want to mitigate these problems and want to allow also faster update procedures. So ESA had the OPSAT, which made this pretty efficient to update software in orbit for testing, and we kind of look for similar procedures. And of course, AI is the current hot topic, and we want to have a platform which can support that. So that's why next comes the Stellar Apps. There, the idea is we have the Stellar Apps project, which is more than just the software framework I'm currently presenting. So in this project, we will have also evolution of the onboard hardware. So this Think 7000 is not the freshest processor anymore, and also not meant to be in space anyways. And then similarly to the SCOSA project, we're currently collecting certain applications we want to prove in or give the opportunity to in-flight testing. And then currently our plan is to use the second extended mission lifetime of the Captain 1 satellite to implement kind of this software application framework and then test it directly in orbit, of course, then on the old hardware. So how does it look like from the developer perspective? So we provide to them a software development environment where they can develop their applications comparably freely. The environment will be similar to what they will see on the onboard computer and have a test system locally. We provide them an API so they can communicate with other parts of the satellites, be it requesting housekeeping data, communicating with instruments or payload systems, or sending telemetry data to the ground station. But our flight software kind of has the rights management to determine if they are allowed to use to send data to another application or not. And this will be part of the negotiation between the project partners and the application developers. So if they have a final version or a first version, they send it to our ground test bench where we do some basic analysis, test the build process, give them feedback or queue it for deployment on the satellite, send it to the satellite, do the deployment procedure, and at some point then schedule the application or the updated application for execution. So for the current SCOSA system, which we want to upgrade in the second year of the Captain 1 satellite, we basically want to keep the flight software of the reliable computing node, let's say, mostly untouched because there's too much risk to update this in orbit. But on the high performance node, we want to split up the flight software from the application software with a strong isolation, and then have these kind of API calls which are, let's say, checked for permissions when one application wants to call to a different one, or if application A wants to take data or command the payload instrument. Also then our, let's say, middleware will be responsible for sending telemetry which comes from an application to the reliable computing node because there's the antenna, and then wrap it into CCSDS push packages so that our ground station can receive it. Then I said we want to enable AI environments, and there are basically two building blocks we want to update individually. So one is the AI model, which is then on board, and also the application which uses the model or applications. Because we want to allow the developers to iterate both of those. So sometimes they want to have time maybe to just improve the performance of the AI model with the data they know directly got from the sensor. And another thing to maybe improve the structure of their application which uses the model. Other than that, we use essentially the same workflow I showed before. So they basically schedule all the updates similarly. There was a big ask for them that they can use, let's say, industry standard tools. So they want to have TensorFlow and PyTorch and not some, let's say, obscure niche product there. I think we had this in a presentation before again that they like to have a laptop with Python installed and in space. And this kind of sentiments we also heard from our developers. Yeah, so we work in other projects with the NVIDIA Jetson. If this is a good platform to do AI performance in orbit, we will have to see. But we also had a nice presentation before about other options, I think. So the applications we currently have in our, let's say, in our mind. So one starts with a simple benchmark. So we have the OBD mark from ESA, which we use as an application. We do some SAE detection and mitigation to measure the performance of our hardware in the radiation environment. ODARIS is kind of this example where we detect the wildfire and make a direct message to the ground station via, for example, an iridium modem. And OBED is basically rescheduling the timeline of commands when there's a more critical event. So if there is a failure of some kind, it will reschedule the plan autonomously without interaction from the ground station. We have the onboard digital twin, which simulates a satellite or a constellation of satellites to so that our ground crew can improve their simulator on orbit, but also test their procedures without having an actual constellation in orbit. And finally enough, the satellite attitude and estimation is kind of this kind of on-orbit servicing experiment, and then also a lot of tests with AI, inference and compression algorithms they want to do from our optical systems people. So this is the short overview, just the conclusions. So we basically want to have Stellar Apps as a one-stop shop for all the different applications we develop at DLR and which want to increase their TRL level in orbit. And we want to bring it in orbit safe and in a secure way so that they have a chance there. And we plan to have the in-orbit demonstration then in the second year of our Captain 1 satellite in 27, 28. And then maybe at some point later, I mean, if there's a Captain 1, there might be a Captain 2 with the updated hardware. So that's it from my side. Any questions?
How detailed is your on-orbit twin?
Bogdan Idria, Visidus Technologies. How detailed is your on-orbit digital twin? Over.
That in detail I can actually do not tell you because I'm the flight software developer and not the one who does the application. But as far as I know, they are at the point where they don't want to simulate it on ground anymore because they say they're the simulation, they have their expectations. And in orbit, they have more, let's say, unexpected events, and then it makes it easier for them to simulate it. So to not simulate it in this regard.
Thank you. Any other questions? Oh, we got one.
Hey, I'm Varun from Stoke. I have a question. Are you able to dynamically load new apps after launch, or are you able to disable them?
So this is the one big point that we want to, because we have this strong separation and isolation of the applications, so that this whole loop is not just once, but multiple times, so that we even have, let's say, experimental software. We have the ability to upload it then the scientists can see, it didn't work because of the reasons, and go the cycle again, improve their software, test again until they have like a stable version or get the scientific output they want.
Oh, that's really cool. Thank you.
Got another one in the back.
Yeah, so the SCOSA architecture mentioned, it was heterogeneous compute, right? Like there was the Xilinx, the ARM-based processors, and the Spark-based processors. I was wondering if that causes difficulty with the load balancing across nodes should one die, like if future things were planned to be more the same architecture everywhere, or if that is more multiple categories would be preserved.
Yeah, so for us, it was when we started the project, and there was a previous project as well, we looked at the market, what is a nice system on chip which is readily available, has some FPGA power, so we can also synthesize a space via IP core on it, and is powerful enough and has a good operating system support. And for the reliable node, we wanted to just make sure that we have something which we know and understand. So far, we have the libraries to abstract away the operating system, which works pretty fine. Where we run sometimes into problems is that our reliable node has, of course, much less RAM memory available. So if we then make assumptions in the overall system setup, which uses more than it will not work on the RCN. But we're working towards this, and in general, it works just fine. Because the reliable node also does not do the heavy lifting on the application side, right? So none of the big let's say, memory-consuming applications will be offloaded to the reliable node on the end. But we have a whole graph. If node 1 fails, then reschedule like this. And if the next node fails, reconfigure again to a different system until maybe it's not feasible anymore.
Perfect. Thank you. We'll take a question from Slack here.
Okay.
George Galashvili says, you mentioned running static analysis and providing feedback to app developers. Are you considering making your analysis tooling portable or directly runnable by app teams to shorten development cycle time?
So my impression is that we would, of course, if it's like a free and open source tool, which does not have a big license, that we make this part of the software development environment so that they can run, of course, their pipeline also locally. But for us, of course, it's then something like that we can say, okay, we are also sure that their software works well enough that we can put it into orbit. But yeah, of course, they should have the ability to have static and dynamic checks as well on their side.
Thank you. Any other questions in the room? We have time for one more. Oh, all right, we got one more.
I wanted to ask, what does it take to port an app to your framework? I saw that there is a library of, like it looks like library of support on the platform, and then there is this distributed tasking framework. So and then that's related to, does this framework use is it based on an existing framework, well-known framework, something like that?
So we have this tasking framework developed in-house and use it in several projects. What it basically does, it creates some executing kernels which execute on data and connects channels which provide the data, and then you can have like a Markov chain, a network of data and kernels. But that's one of the things, right? This kind of also limited our application developers because they had previous applications without this, that they wanted to have more of their own runtime libraries instead. And that's kind of us coming to terms with them for Stellar Apps to improve that and make this easier for them to not need to depend on, let's say, this library. But currently, it's more effort than just porting your normal, let's say, Linux-based application.
Thank you. With that, let's give a round for John. Thank you very much.